Okay, this is a rhombus. What do we mean by a rhombus? A rhombus is a parallelogram where all four sides are equal. Okay, so it looks like a diamond. If you get all the angles to be right angles, you'd also have a square. So you could think of it, a rhombus is to a parallelogram like a square is to a rectangle. So this is a special parallelogram, or a distorted square, if you want to think of it that way. Okay. So since a rhombus is simply a parallelogram, why not use the same formulas for a parallelogram? And the answer is sure, go for it. If you know the base, or if you just have a ruler, you know the base, and if you know the perpendicular distance, which would be this way, in other words, you measure the distance between those two sides, and you take the base times the height, that'll give it to you. But the fact that a rhombus is special, it has all four sides equal, means we can do a different trick with this as well. So here's an alternate way to get the area of a rhombus. What if you know the two diagonals? Say you know this distance and you know this distance. And let's call those D1 and D2, the two diagonal distances, okay? Well, notice that that cuts the rhombus into four identical triangles. And in fact, it's going to produce a right angle here. And so it's going to give you four right triangles. And so since these are at right angles to each other, if I take this length, I could think of that as a base of this triangle, and this could be the height. So let's look at that. If I find the area of one of these triangles and multiply by 4, that'll give it to us. Okay? So if this is D1, this is half of D1. So I have D1 over 2. That's our base of this triangle. Then I have D2 over 2. That's the height of the triangle. Here's your base, and here's your height for this little triangle right here. Okay, so you take 1/2 of the base times the height, and then when you're all done, you multiply by 4, because there's 4 of them. Okay, now just simplify. Think of that as a 4 over 1. If I multiply fractions together, I multiply the numerators together. So on top, I'm going to have 4d1 times d2. And on the bottom, I have 2 times 2 times 2, which is 8. Now I can simplify this. 4 goes into 8 twice. And so we can say the area of a rhombus is 1/2 of d1 times d2. Okay, so it's a second formula. It only applies to rhombuses. It won't work for parallelograms in general, because parallelograms in general, the diagonals will not be perpendicular to each other. This depended on being able to use part of a diagonal as a base and part of the other diagonal as a height, and they had to be at right angles for that to work. So this is a special alternate method to find the area of a rhombus. Do you have to memorize this? No. If you just realize, take half of this times half of this, and when you get, and then multiply base and height and divide by 2, that's the area of one of these triangles, then multiply by 4. You don't even have to use the formula. Just for an example, let's find the area of this particular rhombus without even using this as a formula. We can either use it or not. We can just visualize it as we go. Let's erase all this scratch work here. Okay. Let's just say you have this shape and a ruler. And so if I measure this, I have 1, 2, 3, 4, 5, 6, 7, 8. And this is 1, 2, 3, 4, 5, 6, 7, 8. And so this is 16. So this is 8 by 16. If you remember the formula, just go 8 times 16 divided by 2. Well, half of 16 is 8. This would come out 64, wouldn't it? But what if you don't remember the formula? No big deal. Let's just go for it. What's half of this diagonal? This is going to be 8. This is going to be 4. What's the area of one of these triangles? It's 1/2 the base times the height. 4 times 8 is 32. So this one is 16. What's the area of the rhombus? Multiply by 4, and that's going to give you 64. You get the same area by just working it out. You can always go through the process of breaking these apart and following how we figured out the formula and just use that as the basis for your reasoning instead. Is this easier? Well, if you remember it, it is. If you don't remember it, you're not stuck. You can always go back and say, this is not a magic formula. This came from somewhere. It came by reasoning this out. And since I can split this into 4 small right triangles, I can find the area of each one and multiply by 4. It's that simple. Okay, an equilateral triangle looks simple enough, but the problem is if we're going to find the area, we need to know the base and we need to know the height here. Okay, so the question is, how do we find the height? Well, this particular triangle, let's count the squares. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the length of each side is 10. That means the length of this length in here is going to be half of that, or simply 5. And now we have 2 sides of a right triangle. And we learned last month how to use the Pythagorean theorem. So if I take 10 squared minus 5 squared, since that's the hypotenuse, we have to subtract the 5 squared. That's 100 minus 25, and that's going to be 75. And so now I take the square root of 75, and the square root of 75 is, well, let's see, 75 breaks up as 25 times 3. If you've had some algebra, you'll be able to follow the rest of this. You may have been doing this. If I can break down the 75 as 3 times 25, and you say, aha, I know how to find the square root of 25, so we can break this down as the square root of 25 times the square root of 3. Okay, the square root of the something times something will break up like that. This is simply 5. And so the height here is 5 times the square root of 3. Okay, so what's the area? Base times height. It's going to be 10 times 5 square root of 3 divided by 2. Well, half of 10 is 5, and so it comes out 25 times the square root of 3. Okay? Now, look at the pattern for a second, and we might be able to guess what the formula is, and then we'll go back and actually prove that the formula works. How do you get 25 from 10? Well, we started by squaring the 10. That would give us 100, and this looks like a fourth of that. So this looks like if I have a side length of s, and if I square it and divide by 4, and multiply that by the square root of 3, guess what? That's going to be the area for any equilateral triangle. Okay, let's see if we can prove it directly. I'm going to erase this. This time, for those of you who have had algebra, let's call this length s. And this is going to be s over 2, this distance here. That's a right triangle. And so to find the third side, we square that, and subtract. So I have s squared minus s over 2 squared. And that's going to give us h squared. Okay? Well, s over 2 squared is s squared over 4. This is s squared over 1. How do I combine these fractions? Well, I need the same denominator, so I have to take this times 4 over 4. Now the denominators are both 4. So I have 4s squared minus one of them is 3s squared over 4. And then if I want to find h, I have to take the square root of both sides. The square root of this will be the square root of 3 times the square root of s squared, which is just s, times the square root of 4, which is simply 2. So h is going to be s times the square root of 3 over 2. That's our height. So how do you find the area? Let's use this space up here. The area equals base, which is s, times s times the square root of 3 over 2. So base times height divided by 2. So put another 2 in the bottom. So this becomes s squared times the square root of 3 divided by 4. So our guess was correct, and that's our formula. Okay. How about a hexagon times 6? Find the area of the equilateral triangle, multiply by 6. You don't need to know anything different, except if you actually want a formula for some reason, you can multiply this formula by 6. Notice the 6 and the 4 will cancel. Let's do that here. Here, make myself some room. So if I take s squared times the square root of 3 over 4 times 6, 2 goes into 4 twice, 2 goes into 6 3 times, and so we have 3s squared times the square root of 3 over 2. That's getting a little complicated. It's easier, I think, just to remember this one and multiply by 6. Okay. You can memorize this for short times if you think you're going to need it, but if you ever run into a situation where all of a sudden you need to find the area of an equilateral triangle, you don't really use this one so often that it's worth memorizing. Just remember how we got it. You split it down the middle and use Pythagorean theorem on 1/2 to find the height and go from there. The same kind of comment is true about an octagon. An octagon is like a stop sign. It's an 8-sided figure. And in this case, what we have is each of these here is s. Okay. And what I've done already is I've divided this up into pieces so we can calculate this. The one part that's going to be tricky is look at this little triangle here. Here we have a 45, 45, 90 triangle. So it's these two sides are equal and this side is s. So what are these lengths here? Call each one of those x and use Pythagorean theorem to come up with a relationship between s and x. So if I take x squared plus x squared is equal to s squared. Okay, well that's just 2x squared. Okay, take the square root of both sides. S will be the square root of 2 times the square root of x squared. Then if we want to know what x is, we divide both sides by the square root of 2. So x is equal to s divided by the square root of 2. Okay. In general, when you have a 45, 45, 90 right triangle, one way to remember how to get this easily is just think of each side here as 1, and then the hypotenuse will be the square root of 2. So if you have 1 squared plus 1 squared, it's the same as 1 and 1, you get 2. Take the square root and you get the third side. So in other words, look at this. I take whatever this length is, I have to multiply by the square root of 2 to get the hypotenuse. How would you go backwards? If I know the hypotenuse, I have to go backwards. I have to divide by the square root of 2. And that's where we get this. So if I take this side and multiply by the square root of 2, I get that. If I take this side and divide by the square root of 2, I get that. So if that's s, then this side down here is s over square root of 2. Okay, we're ready to go. We know all the pieces of this puzzle. Let's clear away this preliminary work here. And let's add up the pieces. So first of all, in the middle, let's go back to blue here. In the middle, I have s by s, so that's s squared. Okay. Then I have 4 of these rectangles. The rectangles are, the side length is s, and the side length here is s over square root of 2. And there's 4 of them. So I have 4 times s over square root of 2. Okay. Then I say plus for the triangles. How to find the area of a triangle? It's 1/2 of the base times the height. The base is s over square root of 2. The height is s over square root of 2. And then simplify the algebra here. So this is a problem for students who have had some algebra. These lessons I'm doing are for all through high school. So if you've had algebra, some geometry, any of the above, you should be able to handle some of this kind of work. If you're just starting out, sort of pre-algebra or something like that, this might be more than you want to handle. Go on to the next one. There's some good stuff up ahead, by the way. Well, here goes. This is s squared. This is 4s squared over the square root of 2. And from algebra, you may have learned a trick called rationalizing the denominator. In other words, you don't like to leave square roots of 2 or square roots of anything actually in the denominator. And the trick is you multiply top and bottom by the same thing, because you can. If I multiply by the square root of 2, this simply becomes on the bottom 2. The 2 then cancels the 4, and so this becomes s squared from here. This becomes 2 times the square root of 2 times s squared. And then what about this last one? This is 4 over 2. Well, that's easy. 4 divided by 2 is simply 2. So this is 2s squared over square root of 2 times square root of 2 is 2. So that's simply s squared. So I have 2 of these, s squared plus this. Let's factor out everything we can. So pull out a 2, pull out an s squared. What's left behind? Here I have a 1, and over here I have square root of 2. Is this worth memorizing? Absolutely not. This is something as a puzzle to figure out if and when you need it. All it took to really get going on this was figuring out this little length here. If you know the diagonal is s, then you divide by the square root of 2 to get this other length. And from there, it's just adding up the pieces and simplifying the algebra. So it looks messy, but actually this was the key step. And beyond that, it was just routine. Routine, messy, yes, but still routine. Now, here is a regular polygon. So let's just say it's any kind of a regular polygon. Let's say there's n sides, a whole bunch of sides. We could count them up for this particular one. But instead of doing that, let's just say the length of each side is s. And there's n of them. Now the distance from the center to the midpoint of a side is called the apothem. A-P-O-T-H-E-M. Where do they get these words? It's almost like a radius of a circle, except it would be ambiguous. Are you going to say the distance from the center to the corner, or the distance from the center to the flat part here? The apothem is the distance to the midpoint in here. And sometimes we call this outer one the radius, but again, that's a little bit ambiguous. So let's stick with A. So this is A here. All right. Notice that if there's n of these, we have n triangles that look like this one right here. So first of all, it's going to be n times the area of this triangle. What's the area of this triangle? 1/2 base times the height. Okay. I could say we could leave it like that. So the area is 1/2 n times s times a. But we can actually simplify this a little bit just because. Look at this. See the n times s. What do we have there? Well, s is the side length, and if there's n times the side length, that's just the perimeter. So the area of a regular polygon is 1/2 the perimeter times the apothem. Is that worth remembering? Well, it's worth being able to reconstruct this, and especially it's worth having seen this because it's going to help us on the next step, which really is a big deal. Here we have a circle, and the circle I've drawn inside, so the radius of the circle is what was previously the apothem. It's the distance down to here. Okay. perimeter of the polygon is slightly different from the circumference of the circle, but you can see as n gets larger and larger, so we say as n approaches infinity, the difference between the polygon and the circle vanishes. And so as we get more and more sides, the approximation gets more and more perfect. Let's go back and review. We said the area is 1/2 the perimeter times the apothem. Let's take 1/2 of the perimeter, which is now going to be the circumference, and the apothem is now the radius. And there you have it. So one way of remembering the area of a circle is just remember the area of a polygon. It's 1/2 of the perimeter times the apothem. But this can be simplified. Notice that the circumference of a circle is pi times the diameter. That's the definition of pi. It's the ratio of the circumference to the diameter. So pi times the diameter gives us a circumference. But the diameter is just 2 times the radius. And so we can say the circumference is 2 times pi times the radius. Plug it in. If the circumference is 2 pi r, the area of a circle is 1/2 the circumference times the radius. And what is that? 2's cancel. Area of a circle is pi r squared. I'm sure many of you have memorized this. I'll tell a story, and I won't mention her name because it's probably embarrassing. But I was working with a math teacher in a school in the distant past, and I was thinking of different ways to show that the area of a circle is pi r squared. And I just happened to casually mention in the faculty room, what method do you use to show that the area of a circle is pi r squared? And she just stared at me and said, well, I tell them that the area of a circle is pi r squared. And they learn it. And then they learn how to use it. And they plug numbers in. And that's it. So this person, even though she was teaching math, didn't even herself know any methods of showing that the area of a circle is pi r squared. This method right here, showing that it's based on the area of a polygon, is as easy as any of them. And some of the others are sort of visually appealing too. Let's look at a couple of these methods with GeoGebra. Okay, here we have a regular polygon. You could count the sides, but don't even bother. Let's just say there's a lot of sides, and the same exact reasoning applies no matter how many sides. And so in the limiting case, you could apply this to a circle as well, just by saying it's essentially infinitely many sides. So the red is the perimeter of the polygon, or if you're using this to reason it out for a circle, it's the circumference of a circle. Okay. So if we spread out our polygon, that circumference is now the length of this pattern. Now if we fold it over, we're taking half of the circumference is the length of this parallelogram, and the other half of the circumference just duplicates it up here. What about this distance here? Well, notice that is the apothem. It's the distance from the center to the outside. If we go back and reconstruct it, there it is. So the red is the perimeter of our polygon, and the distance from the tip of one of these triangles to the flat side here is the apothem. So for the case of the polygon, when I spread it out, the length of the pattern is simply the perimeter of the original polygon, and the height of the pattern is the apothem. If I now fold it over, the length of the parallelogram is 1/2 of the perimeter, and here is your apothem. So base times height to get the area of a parallelogram is 1/2 the perimeter times the apothem. If we're applying this to a circle, the length of your parallelogram is 1/2 your circumference, and this would be the radius of the circle. So 1/2 the circumference times the radius. You simplify the algebra and you get pi r squared. Okay, before we go on to the next derivation for the area of a circle, I'd like to show you one of the properties of a triangle. If I change the height of a triangle, notice up here is the computation of the area, and the area changes. Okay, if I change the base, the area changes. But what if I move one of the vertices of a triangle parallel to the opposite side? Notice that the area does not change, and that's because the base doesn't change, the height doesn't change, so the computation of the area doesn't change. So we're free to take a triangle and shear it, and we know that the area is going to be the same. Okay, why did I do that side trip about shearing a triangle? Here we have our polygon, and so we have the perimeter in red, and the apothem is the height of one of these little triangles here. Or if you're seeing this in the limiting case, as we get lots and lots of these, we can think of the red as being the circumference, and this apothem turns into a radius. Okay, so first of all, let's do the same as before. Let's spread it out. But this time, instead of folding it over, let's shear those vertices together. And since all I'm doing is shearing these triangles, I'm not changing their area. So this triangle right here has the same area as this long, thin spike of a triangle, because all I did is I moved the vertex parallel to the base. So for the polygon, it's going to be 1/2 the base times the height, which is 1/2 of the perimeter times the apothem. For the circle, in the limiting case, it's going to be 1/2 the circumference times the radius. All of those methods lead to the same formula. It's just these are different ways to demonstrate why the formula is true. Take your pick, whichever is easiest for you to picture how we got it. And once you know how we got it, remembering that pi r squared is the area of a circle is not that hard. In fact, one way to remember things apart from understanding them, or in addition to understanding them, is to remember little ditties. And so frequently I just remember the area of a circle is pi r squared. No, it's not pi r squared. Pi r round. Cake r squared. Whatever. Pi r squared is the area of a circle. If that helps your memory, then that's all the better.